Good morning, N.A.S students. How are you all, guys? Today we will be discussing acids bases part 4. The graphs or the curves representing the titration reactions. Ladies and gentlemen, as we discussed in earlier slides and videos, that the titration reaction takes place between a strong acid and a strong base. Now, you can represent this reaction using a graph or a curve. Now, when you talk about a graph, you're talking about x-axis, which we call abscissa, and the y-axis is called the ordinate. Now, the graph that shows the variation of the pH values as a function of the volume of either the acid or the base present in the burette. So in math, the pH, the graph of the titration reaction, is the variation of the pH, which means different values of the pH, as a function of the volume of the solution that we have in the burette. So the x-axis or the abscissa is the volume in milliliter of the solution that we have in the burette, and the y-axis, which is the ordinate, it is the value of the pH. Normally or usually, the scale is 1 centimeter for 1 milliliter in the abscissa and 1 centimeter for 1 unit of pH in the ordinate. Now the graph is ascending in case the base is found in the burette, and the graph is descending in case the acid solution is found in the burette. Now each graph has 3 remarkable points to look at, please. The first remarkable point we have in the graph is the initial pH of the solution in the beaker or the flask. Initial pH is the pH of the solution in the beaker or the flask when the burette has not been opened yet, which means that the volume equals to 0 milliliters, meaning that we have not added any amount of the solution in the burette down into the beaker or the flask. So this is called the initial pH. Point number 2, it's the equivalence point, which is the inflection point, and the coordinates of the equivalence points are the VE, which is the volume of either the acid or the base added to reach equivalence, and of course the pHe equals to 7. Remember, the abscissa is the volume of the solution added from the burette in milliliters, and the ordinate is the value of the pH. Now remember that when we have a titration between a strong acid and a strong base, the value of the equivalence point, the pH of course at the equivalence point, is equal to 7. Now the third point is the point at which the curve tends to a horizontal asymptote but remains below pH equals 14 plus log Cb in case the base in the burette, or above pH equals minus log Ca in case the acid in burette. Later we will explain this point furthermore. Now let us just give some definitions here. We read at some point something called the inflection point. In math, the inflection point is the point at which the curve changes directions. Now in these graphs, sometimes they request us to determine the coordinates of the equivalence point using the parallel tangent method. The parallel tangent method is used to determine graphically the equivalence point and to assure that the profile of the curve is correct. In upcoming slides, these 2 points and the horizontal asymptote point will be explained furthermore. Let's please look at these 2 graphs. We have the one on the left. It represents the titration curve of a strong acid with a strong base, and the one on the right, it represents the titration curve of a strong base with a strong acid. Remember guys, when the graph is ascending, we have the base in the burette, and when the graph is descending, we have the acid in the burette. Now, if you notice, I allocated some points on these curves. I allocated points A, B, E, C, and D. A and B, they represent the first section of the graph. BC represents another section of the graph, and this section features the equivalence point, which we call the inflection point, simply because the curve changes direction. Now CD is the last part of the graph, but the one on the left shows that the graph is tending to a horizontal asymptote but remains below 14 plus log the concentration of the base. The line that I have drawn in yellow is the one that represents, in the ascending graph that is, it represents the value of 14 plus log the concentration of the base. So the value of the pH will tend to a horizontal asymptote, meaning that the curve would just simply become parallel to the x-axis, but this curve will never touch the yellow line. It has to be below that yellow line. Remember, the yellow line is the line that we call the value of 14 plus log concentration of the base. Now the graph on the right, it has also the points A, B, E, C, and D. A and B, it's the first section where the pH decreases slightly. B and C is the section of the curve, or the part of the curve where the pH value decreases very sharply, and this part features the equivalence point denoted by E. And CD is when the pH decreases slightly and the curve tends to a horizontal asymptote but remains above minus log the concentration of the acid. If you notice, ladies and gentlemen, that the pH value at equivalence is equal to 7, simply because the titration between a strong acid and a strong base has a pH value at equivalence equals to 7. Now please let me just recap the part of the curve where the curve tends to a horizontal asymptote in both graphs, the one on the left and the one on the right. In the one on the left, we have this yellow line that indicates the value of 14 plus log the concentration of the base, and the curve, as you can see, it will never touch that line. It has to remain below it. On the curve on the right, you see the section CD. The curve is tending to a horizontal asymptote, which means that it is just becoming parallel to the x-axis, but as you can see, it will never touch the yellow line, and this yellow line indicates the value of minus log the concentration of the acid. Let's describe the two curves, please. Let's start with the ascending graph or curve. Part AB, the pH increases slightly as seen in the previous slide. BC, the pH increases sharply, and it has an inflection point, which is the equivalence point. And CD, the pH increases slightly again, and the curve tends to a horizontal asymptote but remains below 14 plus log concentration of the base. For the descending graph, the AB, the pH decreases slightly. BC, the pH decreases sharply, and it has an inflection point, which is the equivalence point. CD, the pH decreases slightly again, and the curve tends to a horizontal asymptote but remains above minus log concentration of the acid. Let's explain the parallel tangents method. Remember, like I said earlier, the parallel tangents method is a method used graphically in order to determine the coordinates of the equivalence point. Now look at this graph or the curve drawn in blue. On this curve, we have two tangents A and B. Now, the tangent C is the equidistant parallel between the two tangents A and B. What is meant by equidistant parallel? Equidistant parallel means that the distance between A and C equals to the distance between C and B. Now, the point at which the equidistant parallel to A and B touches the curve is the point that we call the equivalence point. In this case, as you can see on the graph, the pHe, which is the ordinate value, equals to 7, and the 25 is just simply the volume of the base added to reach equivalence. So the coordinates of the equivalence point are very much determined graphically by the parallel tangents method, in this case as seen on the slide. And the coordinates are VBE equals 25 milliliters, which is the value on the abscissa or the x-axis, and of course the PHE equals to 7 on the ordinate or the y-axis. The parallel tangents method, ladies and gentlemen, is also used in order to make sure that the curve is simply drawn in the right manner. This concludes the notes on the acids and bases, ladies and gentlemen. Thank you so much for hearing me out.